We are going to talk about graphs and derivatives. And we're going to begin with this question: where is the function f of x? And I've given a formula for f of x here. It's a polynomial. Where is this function increasing and where is it decreasing? And what does it even mean to ask where a function is increasing or decreasing? Now, in Desmos here, I've graphed our function f of x equals x cubed minus 6x squared plus 9x plus 2. And notice the function is initially going up, and then it's going down, and then it's going up again. So we say the function is increasing for a little while, and then it's decreasing, and then it's increasing again. So when we ask where is the function increasing or decreasing, what we're really asking for is along the x-axis, on what open intervals is the function increasing or decreasing. Now notice that at 1, the function kind of peaks out here. It has what's called a local maximum. And then at 3, it has a minimum. But between 1 and 3, the function is decreasing. So the function is decreasing on this interval 1 to 3. Now it's increasing over here. It's increasing on the interval from negative infinity all the way up to 1. And in fact, I've drawn these intervals here in different colors here. So on this blue interval from negative infinity all the way up to 1, the function is increasing. On the open interval from 1 to 3, the function is decreasing. And then on the open interval from 3 to infinity, the function is increasing again. Now, a question that we could ask though is, suppose I had just given you the formula for this function f of x and I had not drawn the graph. How could we tell just based on the formula where the function is increasing or decreasing? Well, the key thing to observe here is that at any point here on this interval 1 to 3 where the function is decreasing, notice that the slope of the tangent line is negative. In fact, I've drawn in a tangent line here at a point, it looks like it's 1.5 here. Notice that f of 1.5 would be this number up here along the y-axis, but f prime of 1.5 is the slope of this tangent line, and notice it's a negative slope. And that's true for any number between 1 and 3. It has a negative slope. Okay, now once we get beyond 3 here, it has a positive slope. So where the function is increasing, the f prime is positive, right? It has a positive slope. And same thing over here, has a positive slope. But between 1 and 3, it has a negative slope. So to find where f is increasing or decreasing, we need to look at where f prime, the derivative, is positive or negative. Now notice we do have 2 points here where the slope is 0. So notice that 3, the slope is 0. So f prime of 3 is 0. Also at 1, f prime of 1 is also 0. And those numbers 1 and 3 are called the critical numbers of the function f. So a critical number is a number where the slope is 0. It could also be a number where the slope doesn't exist, so it's not differentiable. So it could, if it had a sharp corner, for example, that would also be considered a critical number. I'll mention a little bit more about critical numbers in just a minute, but notice that at these critical numbers, we have a local max and also a local min. It's called a local max. It's not the highest point on the entire graph, but just locally, it's a local maximum. So again, the key observation is that to find where f is increasing or decreasing, we need to look at where f prime is positive or negative. So again, here I've written it out. Notice that to find where a function f is increasing or decreasing, we need to find where f prime is positive or negative. So how do we do that? Well, let's go ahead and work on this function that we've already been considering here. How do we find where f prime is positive or negative? Well, let's go ahead and find f prime of x, right? F prime of x is 3x squared minus 12x plus 9. Now, how do we find where this is positive or negative? In other words, what inputs for x would make this positive and what inputs for x would make this negative? Well, the key thing we need to find first in order to do that is to find what inputs here for x would make this be 0. So essentially what we need to do is to factor this. So let's factor this by first of all factoring out a 3. Let's write this as 3 times x squared minus 4x plus 3. And then let's factor this polynomial in here. And what we get is, let's see, it'd be x minus 3 times x minus 1. If you FOIL this out, you get this. So what are the zeros of this? Well, what numbers make this 0? Well, notice because of this factor here, we have x equals 3 is a 0. And this one here, we have x equals 1 is a 0. So 3 and 1 are the zeros of f prime. Now, remember, our goal is to find where f prime is positive or negative. So what we're going to do is draw a little number line here, and we're going to label the points along the number line 1 and 3. Now, I'm not going to label all the tick marks. So 0 would be here, 0, 1, 2, 3, 4. I'm not going to label all the numbers here, but just 1 and 3 will label. And we're going to be looking at f prime. Where is f prime positive or negative? Well, we notice that at 1, f prime is 0. So I'm going to put a little 0 there. And then at 3, f prime is 0 as well. So in other words, f prime of 1 is equal to 0. F prime of 3 is equal to 0. What about if we took a number between 1 and 3? So maybe like 2 or 2.5. Just pick any number that's between 1 and 3. Is f prime going to be positive or negative? Well, we could plug it into this original formula here, but I think it's easier to plug it in here. If I plugged in a number like 2, well, notice this would be positive. 2 minus 1, that's positive. This would be negative. 2 minus 3 is negative, and of course 3 is positive. So if we multiplied a positive times a negative times a positive, notice we get a negative. Okay, for any value between 1 and 3, so not just 2, but 2, 2.5, 1.5, any number between 1 and 3, it's going to be negative. If we picked a number that was bigger than 3, so let's say like 5 or 4.3, just any number bigger than 3, if you plug it into each of these x's here, we would get a positive number for this factor. So like 5 minus 1, that'd be 4, that's positive. And 5, if we plugged it in here, 5 minus 3, that's 2, that's positive. And this is 3, that's positive. So we get a positive times a positive times a positive, that's positive. Okay, so no matter what number we pick out here, we're always going to get positives. And if we pick a number less than 1, so any number less than 1, so like 1 half or 0 or negative 10, if we plugged it in here, we're going to get a negative number. If we plug it in here, we're going to get a negative number, and 3 is positive. So if we get negative times positive, that'll be positive. So that's true for any number out here. So what we've drawn here is what's called a sign chart. Okay, this is a sign chart for f prime. So f prime is positive here, then it's negative, then it's positive. What that really means is that since f prime is positive over here, the original function is increasing. And since f prime is negative in this interval, the original function f is decreasing. And since f prime is positive over here, f is increasing. So f is increasing, then decreasing, then increasing. So notice we've really answered our question. We can now say where the function is increasing and where is it decreasing. Well, it's increasing on the interval negative infinity up to 1. And it's also increasing on the interval from 3 to infinity. It's increasing on these two intervals. Now, where is it decreasing? Well, it's decreasing on the open interval from 1 to 3. And by the way, we're always going to use open intervals when we talk about where the function is increasing or decreasing. So again, notice what we did. To find where f is increasing or decreasing, we look at f prime. We want to find where f prime is positive or negative. To do that, we found our derivative f prime, and then we factored it. And once we factored it, we came up with these two numbers, 3 and 1. Again, these numbers are called critical numbers. And these two numbers, they're going to partition the whole real line into these three intervals, these three subintervals. And we need to decide on each subinterval, is f prime positive or negative? And we can do that by picking a number in each interval and plugging it in for x and deciding, is this positive or negative? So we developed this sign chart for f prime. And the sign chart tells you where the original function is increasing or decreasing. Okay, so it's going up, then down, then up. Now, I've used this phrase critical numbers a couple times. What is a critical number? Well, a real number c in the domain of f such that either f prime of c is 0 or f prime of c does not exist. So when f prime of c is 0, the slope of the tangent line is 0. When f prime of c does not exist, that means we have like a sharp corner at c. Or it would also be the case if you had a vertical tangent line, right? If the slope were infinite. This is called a critical number of f. So in our previous example, the numbers 1 and 3 were critical numbers. And critical numbers help us determine where a function is increasing or decreasing because they help us to partition the real line, the interval minus infinity to infinity, into subintervals where the function is increasing or decreasing. Now, critical numbers are also important because they are candidates for where local extrema may occur. So like a local maximum or a local minimum could occur at a critical number. Now, to see whether a particular critical number gives a local max, a local min, or neither, we use something called the first derivative test. So, what is the first derivative test? Well, it's actually pretty easy to understand. The first derivative test is going to test whether these critical numbers, so in our original example here, the critical numbers were 1 and 3, whether those numbers give us a local max, a local min, or neither. Well, notice that 1 gave us a local max. And how could we tell that based on the sign chart? Well, notice the original function is increasing and then in decreasing, right? So we have pluses to the left of it, minuses to the right of it. So it's increasing, then decreasing. So we have a local max at 1. And at 3, we have a local min because to the left of it, the function's decreasing. To the right of it, the function's increasing. So it's going down and then up. So at 3, we have a local maximum. So that's really all the first derivative test is. You just look at a sign chart for f prime and look, where's the function increasing and decreasing. Well, if it's increasing to the left of it and decreasing to the right of it, it goes up and then down. We have a max. If it's decreasing to the left, increasing to the right, we have a min, right? It's going down, then up. And you could see that here. Notice at 3, we have a local min because it was decreasing to the left, increasing to the right. At 1, we have a max because it's increasing to the left, decreasing to the right. So the first derivative test tells you that if you have a situation like this, where we have pluses to the left of a critical number and negatives to the right, we have a local max. Now, by the way, sometimes you'll see ND written right here instead of 0. So ND means not defined. So in that type of situation, instead of the curve rounding off at the top, that means you just have a sharp corner at the top, so like a V. So for example, like an absolute value function has a sharp corner in it, right? So imagine a sharp V like this, we would also have a local max. So if it's either 0 or ND, so again, ND means not defined. You could think of it as not differentiable is another word for it. But C is this number that's in the domain where the derivative is either 0 or not defined. We're going to get a local max in this situation. Now, in this situation right here, where it's decreasing then increasing, right? So f prime is negative here, positive here. The original function is going to have a local minimum. And again, this could either be 0 or nd right here, not defined. Now, when we say not defined, we don't mean that the original function is not defined at c. In fact, c has to be in the domain of the original function. F has to be defined at c in order to be a critical number. But what we mean is that the derivative, f prime, is not defined at c. Now, we could also run into a situation like this where we have a critical number, a place where the slope is 0, but it's pluses to the left and pluses to the right. You might think, well, how could that happen? Well, you could have a function, for example, that does something like this, almost like an x cubed type function, where we have a point there where the slope is 0. Okay, one point where the slope is 0, but it's increasing to the left, increasing to the right. Well, what do we have there? Do we have a local max, a local min, or neither? Well, we have neither. Okay, so if it has the same sign to the left and to the right of that critical number, so it's pluses to the left and pluses to the right, for example, then we have neither a local max nor a local min. And same thing if it's negatives to the left and negatives to the right. So for example, you could have a function that does something like this. Maybe there's a point where the slope is 0, but to the left it's decreasing, to the right it's decreasing. Well, again, at this number here, at this number C, we don't have a local max or a local min. So we have neither a local max nor a local min. So again, these critical numbers are candidates for where local extrema might occur. Okay, but you could have neither a local max nor a local min. Just because you have a critical number, it doesn't guarantee that you'll have a local max or a local min, but it's a candidate for where you could have one. And that is called the first derivative test. Now, going back to our original question, we could ask, what are all the local extrema? So notice at 1, we have a local max. At 3, we have a local min. But what is that local max and what is that local min? So looking at our graph here, notice that it's actually the point 1 comma 6 that's at the top here. So what we'd say, it has a local max of 6, but it occurs at x equals 1. And likewise over here, we have a local min of 2, but the min occurs at x equals 3. Now, how could we find those numbers 6 and 2? Well, we basically just plug our 1 and 3 into the original function f. You don't plug them into f prime because f prime of those numbers is going to be 0, but you plug them into this function. So if we look at f of 1, if we plug in 1 everywhere we see an x here, we're going to get 6. You can try it for yourself. If you plug in 3 everywhere you see an x here, it's going to give you 2 as a result. Now, the way that MyMathLab would word this is it says the function has a local minimum f of blank equals blank. Well, remember that f of 3 is where we had our local minimum, And remember the f of 3, if you plug it in here, you can see f of 3 is 2. So f has a local minimum, f of 3 equals 2. Now, I actually don't like the way this is worded. I would word it a little differently. I would say the local min is 2, and it occurs at x equals 3. But the way it is in my math lab, the function has a local minimum, f of, and it leaves a blank there, equals blank, and you have to fill this in. F has a local maximum. Well, remember it had a maximum at 1, and if you plug it in for yourself here, you can see f of 1 was 6. So we can say f has a local maximum, f of 1 equals 6. Now, I'll do a few more examples in the next video.